Good. How are you? Yeah, doesn't look like that's going to go away anytime soon either. I know. I looked at the prediction and there was snow like 6 out of 7 days, it seemed like. You never know, but it's definitely not going to be warm. Yeah, I mean, the dean was saying what a great job they had done with the ice removal, but there's a lot of ice in like well-traveled sidewalks out there. Is that right? Okay. Let's 212. Okay, so I see Grant online and Josh Cole and Hunter. There you are. Nafiz is on there. Let me just get started with the rest of you here. Abby Carter. Now, are you the one who said you were out and okay, so you're back now. Just trying to put a name to an email. Okay, good. Tyler Davidson, good. Feng Yue, good. And Amelia is gone. She's at a cross-country meet. Jaden Gilmore, Hunter, I saw. Pat Newcomb Maddox, okay. Edward Lee Major, right. Manasa, okay. Sam Polio, all right. Jacob Ratliff, all right. Arthur Ray, Asa Smith. I feel like I saw that he dropped, but I didn't mark it on here. Okay, well, a little question mark there. Austin Stallings, Sarah Tahanasab, all right. Evan Wallace, Kate Williams, all right. Dylan Wilson. Okay, anybody I didn't call? All right, good. Hopefully, it looked like a couple of people dropped, so I'm hoping we're all going to be good to fit in here from now on, and hopefully I won't have to worry about that anymore. I'm always going to default to if for some reason something goes horribly wrong or somebody who's normally home comes in, I'll just put this seat over in the corner 6 feet away from everyone else, and then we'll start worrying about it again. Anybody having trouble with websites? My website, posting on the website? Seemed like I saw the numbers where almost everybody was posting on there. I think there were 24 comments, at least from the beginning of chapter 2. Quest. Anybody having trouble with Quest? I'm trying to look every once in a while and approve enrollments. It's sort of weird that I have to kind of like just click accept, accept, accept. But as of yesterday, I had approved everyone. Chapter 2 homework is up. We certainly haven't, in the videos you watched, we haven't talked about nearly all of it, but I tried to give you an indication in the email yesterday about which ones you were sort of okay to do and which ones we need more discussion on. So we'll do some discussion of that today. I don't know that we'll finish today. Probably at the beginning of Monday is more like when we'll finish chapter 2. So I've also got on the website chapter 3 for reading over the weekend. And I think I decided based on that one student comment that it's fine with me as long as you have it, your reading response posts done by 8 a.m. of the morning that we're having that next class. So I have the dates for this weekend are today through Sunday, but it should be completed Monday by 8 a.m. If you're a real night owl, that's fine by me. Question?
So like for the comments, I know that the criteria is kind of vague, just like whatever you wanted from it. Is it just responding and like putting questions in there that you had during the reading? Like is there like how's that being graded, I guess?
Yeah, I mean, the answer is I haven't started grading it, but I know how I've done it in the past, and any of the following are okay. You can put questions down. Just try to make them, put enough stuff in there so I can understand the context. A very short sentence is sometimes hard to, really for me to understand what you're getting at. And generally, like, just echoing someone without adding anything who's already posted on there is probably, a little bit light on that. Commenting back, I should have said, on other people's posts is fine too. So sometimes people just think, well, maybe I took physics before in high school, and if this stuff is the beginning, I'm comfortable with it. But I can respond to a couple other people's questions and try my best at answering their stuff. Or anything that it makes you think of that the author didn't talk about, questions that it raises in your mind, that's fine too. I certainly don't promise to answer all those. I'll put a few of them up, usually every day. where there's relevant material, and it's just a grab bag. Some of them are ones that I saw questions repeated several times, and some of them just bring up interesting points that maybe are common confusions. So I probably will try, usually people are really good at doing it at this point in the course, and they'll write paragraphs up there, and then it starts dwindling by about a third of the way through the course. So when it starts dwindling, I may put a few examples up there and say, this one's not enough. This is sort of ideal. This person may be going over the top, which is fine by me, but you don't have to write, a mini essay every day. Shouldn't be a burden, but try to sort of sink your teeth into it and think, what are the places where I really thought, what is the author talking about? Or the author is not making sense in light of something that he said before, or what we're doing in class doesn't make sense in light of what the author is saying here. Anything else? Gotta remember to stand in front of the camera. Okay. Good. I don't think I have any other announcements. We will probably a couple of times be using these voting cards. So hopefully remember to bring that with you. I will also sometimes forget, for those of you who are on Zoom, I know that you can pin the video. So if I start writing up here and it's in the small window, you can make it big. But I would like to have it so that the recorded video actually shows it big. So when I post it, if you want to go back and see what we did exactly on that day, it's big. So if you see me writing up there and I haven't switched to the camera that's showing the board from the slides, because I try to use a lot of slides since we're doing stuff online too, just unmute and tell me, or someone in the class notices that I haven't switched and it's still showing the slides, but I'm writing on the board. Help me out and I can just quickly switch the camera. Okay, so what I want to do at the beginning is, I know it was a little bit, I don't know, I kind of like the videos. I probably do a better job of explaining things in those videos than I can do in class, because I carefully think about how I'm going to craft the argument, and there's no distractions either. But I'm going to try to recap a few things that I think are important from those sections, just so you have a chance to ask questions if you have them. Okay, so let me share my screen now. Okay. And let's hope my pointer works. I've got so many moving pieces here. There it is. All right. Okay, so one of the things you saw, this was just one, I'm not going to talk about changing units. I'm assuming most of you are pretty comfortable with that, but there was an example that involved a cube or something like that that was a little bit tricky. If you're having trouble with that, or if you need more help with it, certainly come and ask me about it. It's my assessment that most people in this class just kind of got that pretty well from high school. One thing that I will be doing that's probably a little bit different than the way the author writes equations in the book or fills numbers into the equations is, I'm lazy. And you'll notice the author always puts units next to every quantity with dimensions. So if he tends to use SI units more than anything else. So if it's a speed or a velocity, he will put a meters per second next to it, right? Acceleration in meters per second squared, that kind of stuff. It's next to all the numbers in every equation, because if you write a book, you may as well do it right. When I'm writing things on the board, I'm going to be tempted, and I will drop those units if we're under the agreement that in that problem, we're just going to stick all to SI units. And the reason that helps us is because of this thing that was mentioned at the end of the chapter 1 video on dimensionally balanced equations. Every equation in the book is what we call dimensionally balanced. And that means the dimensions of the left, in this case, this is an X position, right? An X coordinate. So this has dimensions of distance, right? If this is an equation that you see written in the book, I've already lost control of my pointer, then the dimensions on the right-hand side of the equation should be the same dimension. So if it's distance on the left, it's distance on the right. What that means is, if I plug into this big mess over here, which we're going to encounter today in class, this is a position, so I'm going to put it in meters. That's a velocity. I'm going to put it in meters per second. That's a time. I'll put it in seconds. All those are SI units, International System units. A in meters per second squared. This is not working well. All right, there we go. If I put in all SI units on the one side of the equation, then I know I'm going to get SI units out on the right-hand side. And because it's dimensionally balanced, if I put in all that meters per second squared over here and meters per second squared, I know this is a distance and it's going to come out in meters. So I'm just going to, when I write it on the board, I'm only going to write the numbers without the units and say, in this problem, we're going to use all SI. And I know I'm computing a velocity, so I can just throw a meters per second on it at the end of the problem and not have to carry all those units through like the author does. Okay, and the same thing for other kinds. Here's one that's solved down here. It's solved for a velocity. So I plug in this. I don't even have to think about it. If it's all in SI units, then I know I can put a meters per second on that because it's a velocity at the end of the problem. Okay, so two of the big ideas that were introduced in the sections that you were looking at were velocity, average velocity, and instantaneous x velocity. If something's moving along the x direction, I tend to call it x velocity. The author of the book doesn't put, but it's helpful because we're going to have y velocities and z velocities later on. Nobody really cares about the average x velocity. It's sort of a stepping stone to getting to the x velocity, which is instantaneously right now, how fast and in what direction am I going? But the average x velocity is sort of easier to compute. It's like how you know how to calculate a speed. You say, how far did I go divided by the amount of time it took? Delta x, the displacement, divided by delta t. That's average x velocity. And average x velocity, of course, is defined for a certain period of time, here between maybe these two times. And you can see from the graph up there that delta x is how much, if I'm plotting a graph here of x versus t, so I'm saying what is the x coordinate for each time of an ant that's moving on the x-axis or something like that. Delta x is its displacement between the initial time and the final time. That's this distance right here. And delta t is how much time elapsed. And you can see, because you know something about slopes and rise over run, that delta x over delta t can be interpreted as the slope of this secant line, shown in red there. And nobody cares about the average x velocity. What everyone is concerned with is the x velocity at this time or that time or another time, right? So I may want the x velocity, how fast and in what direction am I going right at this time? And to do that, what we do is just take that average x velocity between two times that are really, really, really close to the time that we're interested in, okay? And somewhat confusingly, you've seen this before if you've done calculus, but this is a non-calculus based course. That process of making the change in time really small is written in this limit notation, but don't be off-put by it. It's just the average velocity taken over a very short period of time. And you make sure that that short period of time includes the time that you're interested in, and then it will tell you essentially what the instantaneous velocity is. And there was a little construction, probably with a little GIF in there that showed how the secant line, when you make this point get closer and closer to the other one as the times get closer and closer together, the secant line turns into a tangent line. And so if we have a graph of x versus t, and we want to know what is the velocity at a particular time, say this particular time here, what I do is go up to the graph and draw a tangent line to the graph. Okay, a tangent line means a line that just touches the graph at one point. I won't be able to show this to the folks on Zoom, but let me take a ruler here and say, if I'm trying to get the velocity at this particular time, I would try to make a line that's tangent to the graph right above there, touches it right at that point. So that would be a negative velocity at that particular time because the slope of the tangent line is negative. It went from a slope of a secant line to the slope of the tangent line. How about right where this peak is? At that time, the tangent line is horizontal and the slope is 0. And therefore, I would say the instantaneous x velocity is 0 at that time. Okay, over at this time right here, I have to attach a tangent line there, and then the velocity is the slope of that tangent line. Positive slopes go up like this, 0 slopes are like this, negative slopes are like that, right? So there's a positive slope at the point I was pointing on there, and therefore there's a positive slope velocity at that time. Okay, that's velocity. Most people have a pretty good intuition about velocity. Velocity just means how fast are you going and in which direction. And in this case, when we're just talking about x motion, the which direction is told by the plus or minus sign for the velocity, right? If I say this is the direction of plus x, and I have a positive x velocity of 3 meters per second, right? Plus 3 meters per second, that means I'm moving in the plus x direction towards plus infinity at a speed of 3 meters per second. If it's negative, doesn't matter whether I'm over here in the positive region of the x-axis or the negative region of the x-axis. If it's a negative x velocity, it means I'm heading towards minus infinity on the axis there. Okay, that's just a little recap of velocity. You saw a worksheet where, usually I would demonstrate this in class. We had a mass on a spring that's bouncing up and down under the influence of gravity. And I sort of originally drew what I thought the x versus t graph might look like as this thing oscillates up and down through 2 complete oscillations there. And the question is, how would I construct what the x velocity versus time would look like? Or I guess I am calling it x here. Can I bring this over here and show me drawing on this? I don't know how well you guys on Zoom can see this bright screen, but we'll try it that way. Let's just try to construct a few numbers, locations on this graph. I'm just going to put some points on this graph. I want to say right at t equals 0, what's the value of Vx? Is it positive, negative, or 0? Can anybody help me think about that from the graph? Positive, negative, or 0, just a hair above t equals 0. Right at this point, where should I start? Up here, down there, or right at the value of 0? At 0, what are you looking at to say 0? Yes, and so what we're supposed to do is say, I want to find the velocity there. I go up to the graph, well, we're already on the graph, and I attach a tangent line at that point. It looks like it's pretty horizontal right there, right? That's not tangent at t equals 0, but if I slide it down to the point where it would just touch it at t equals 0, it looks like it would be horizontal. That's the slope of the tangent line that's attached to the curve at t equals 0 is the height of this curve down here. So the height of this curve should be 0. Okay. What happens to the slope of the tangent line as t gets a little bit bigger? It starts to become positive, doesn't it? Little positive, little more positive, little more positive. It's probably the maximum positive slope sometime around right here, right? So if I go down to that same time down here, that's when the height of this curve would be maximum. The slope of the tangent line up here gives me the height of this curve down here. And negative values means negative heights. I go below the t-axis. Okay, so the value was 0. Value becomes a little bit positive, a little bit more positive, a little bit more positive. So this certainly isn't any sort of definite procedure, but I'm just trying to qualitatively explain it. Okay, and there it is, the biggest it ever gets right there. And then it's got to start going down. And so, I might change my mind a little bit here. It seemed like it was going up, but since it's about to start going down, it seems like we've reached the top of a hill there. We're at the highest point we're ever going to get at. The slope of the tangent line is as big as it's ever going to get. As time goes forward, it starts becoming smaller, smaller, smaller. Slope of the tangent line right at this time becomes 0. And that means the height's going to go back to 0 at that time. Height of this curve goes back to 0. It's probably got a little bit of a curve on top. Okay, then the slope of the tangent line starts to become a little bit more negative, more negative, more negative, maximum negative, right? Probably there, probably at this time. That's when its height should be maximum negative. That's probably when it's at the lowest point it's ever going to get to. And not surprised, you could continue that construction. That's one complete period. That gets us from there to there. And then, of course, it's going to repeat again after that. In the lab that you're going to do next week, you're going to do this kind of stuff. Well, I won't say ad nauseum, but you're going to do it a lot. Hopefully, if you have me or if you have Dr. Falco, we'll do a lot of examples at the beginning, just asking for you guys to call out how to continue the graph. And then you're going to do some stuff where you're making tracks that cause a marble to move in a certain way with a certain velocity as a function of time. And you've got to maybe draw the position as a function of time, or you've got the position versus time and you draw the velocity, kind of like here. So we'll get some practice with that next time. Any questions that come up in this particular example here? Given that we're going to practice it some more, you know, we could draw graphs all day and they still can sometimes seem confusing. Uh-oh, I've drawn on my screen, so I've got to erase it. Okay, acceleration. So the nice thing about acceleration is if you buy the whole construction of given a graph of position versus time, we know how to construct the instantaneous velocity. That's the slope of a tangent line attached to the curve at that time. The relation of position versus time to velocity is the same as if I draw, this looks like the same graph, but I've relabeled axes. This is now velocity of the object versus time. It has a positive x velocity there. That means it's going in the plus x direction towards plus infinity. Positive, 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 positive. Notice this object, if I take this at face value, this velocity versus time graph is describing something that's always going towards plus infinity. It never turns around. If it turned around, the velocity, the x velocity would have to be negative. That would be below the t-axis at some point. So it may be speeding up and slowing down and speeding up and slowing down, but it never changes direction. It's always heading toward positive infinity. Okay, same kind of idea here. Nobody cares about the average x acceleration. It's a stepping stone to get toward the x acceleration. Right now, how fast am I accelerating? How fast was I accelerating a second ago? And to do that, the construction is exactly the same. The average acceleration is delta Vx over delta t, which can be interpreted as the slope of a secant line. And if we want the instantaneous x acceleration, we just take that time period close together so that it surrounds the time we're interested in. And if you look at the graph, you'll see that that secant line will turn into a tangent line. So it sounds like a lot to say, but the slope of the tangent line to the x versus t graph at a certain time is the x velocity at that time. Similarly, the slope of the Vx versus t graph at a certain time is the x acceleration at that particular time. Okay, so the construction is easy enough. That doesn't mean you have very good intuition about acceleration. And I think several of you asked questions about the confusingness of acceleration. And the last kind of reminder slide I wanted to show was this one where I just demonstrated a lot of things that sound a little bit crazy. Part of it is just the weird language that has become embedded over time. It kind of sounds like positive acceleration. If I have positive x acceleration, it kind of sounds like I should be speeding up, but that's not necessarily the case. I could have positive x acceleration and be slowing down. I could have negative x acceleration and be speeding up. And the way I told you to kind of, at least I like to think about getting the sign of the acceleration right, if you know how the object is moving, is to think about which way the velocity is trending. If the velocity is trending more and more, it's doing the best it can to get to a bigger and bigger positive velocity. That's a positive x acceleration. So for example, nobody's going to be confused if I say, there's plus x, I'm moving in the plus x direction, so I've got a positive x velocity. What does a positive x acceleration mean? Well, it makes sense. I'm going faster and faster in that direction, right? But if I'm moving in the negative x direction, and I've got a positive x acceleration, that means I should start trending towards moving that way in the positive x direction. So if I'm moving in the negative x direction, how do I start going in that direction? Well, I first got to slow down and come to rest before I can start moving in that direction. So I would say slowing down in the negative x direction is my velocity trending towards the positive x direction. If that helps you remember it. Similarly, slowing down in the positive x direction is my way of trending towards my velocity going towards the negative direction. And so that would be a negative x acceleration. If that helps you reason it out a little bit better, that's fine. I'll try to remind you a little bit more of that as we're going on. Confusingly enough, this always confuses people. Deceleration always means you're slowing down. Whereas acceleration, which sounds like the opposite of deceleration, but it's not at all. Acceleration just means your velocity is changing. So if I'm speeding up in the positive direction, I'm accelerating. If I'm slowing down in the positive direction, we would still be right in saying I'm accelerating. If I'm speeding up in the negative direction, I'm accelerating. If I'm slowing down in the negative direction, I'm accelerating. But it's only when I'm slowing down, I'm moving less and less quickly, that we would say I'm decelerating. It means you're coming closer and closer and closer to being at rest. So those words, even though they sound like they're the opposite of each other, they're not the opposite. Acceleration just generally means your velocity is changing. You're not moving with constant velocity. Whereas deceleration always means you're slowing down, getting closer and closer to rest. All right, questions on those, which were things I think you saw in the videos last time. All right, let me move this back and away from the screen and see if we can get kind of a good view here for writing on the board. But let's stick with the slides for a second. Oh, I forgot, I put some of your reading responses in here. So let's just look at a grab bag of these that had to do with the early chapter 2 stuff. A bunch of people mentioned they were confused about what translational motion means, and I didn't use that word in the video, but generally translational motion means you have an object. Here my object is a block. And in undergoing translational motion, it means it's not going to rotate. If it were squishy, it's not going to compress or expand. You know, if it were made of springs, it should just keep its exact same shape and only move around. So if this block goes like this, from here and then up here and then over there, we would call all of that translational motion. It didn't rotate at all. It just sort of kept its same orientation and shape and only moved around to a different location in space. This is also translational motion. And you might say, well, why do we care? Or when does that come up? You know, if this object is going down a ramp like that, we would call that translational motion. Whereas technically, if I have a bowl, maybe a bowl with a slick surface, and I let it go, and it goes like this, that's technically not translational motion because it's rotating as it goes down to the bottom of the bowl. It's got to keep its same orientation. Now that we might ignore that rotation sometimes, but that's what translational motion means. Sometimes people say an object is behaving like a particle. We would call it a particle if it only moves in translation. Does instantaneous speed always equal the magnitude of the instantaneous velocity, even in 2 and 3 planes of motion? I mean, I put these on here this morning and I can't remember exactly why I chose this one, but the answer is yes, it is the magnitude. The answer, we haven't talked about 2 or 3 motion in 2 or 3 dimensions, right? A fly flying around on a weird path in 3 dimensions. We won't do anything that complicated, but we'll throw objects in the air and they'll move along like parabolic shapes. That's a kind of 2-dimensional motion. You have to know what magnitude means in that case. But in 1-dimensional motion, magnitude just means, well, if it's got a minus sign, throw it away. If it's positive, you just keep it. So for right now, all we have to do is throw away the minus signs, but it won't be so simple when we get to 2 or 3-dimensional motion. That's chapter 3. Is it automatically a negative displacement when the particle is moving to the left? Sounds right, but you know, that's just because we usually think of to the right as the positive direction, right? I mean, I would say, here's my left, here's my right. If I label this as the plus x direction, and an object goes from here at an earlier time to there at a later time, I would call that a positive x displacement. But it could still go to the right, and I might have said, well, you know, I really wanted to take the plus x direction in that direction. Then it would be a negative x displacement. So it all depends on your axes that you've chosen. And you're free to choose any axes always that, you know, either make your life easier or is just your preference and habit. You know, most of the time, if something's moving to the right, we like to call to the right positive. So I'll try to do that when it makes sense. I'm asking this, let's see if I understand this. I'm asking this because Giancarlo said the y-axis is usually, but not always, used for vertical motion. That's true. I just put this on there to make the point that I don't have to call, when we're moving in 1 dimension, you don't have to call this x. I could have said, hey, here's something moving to the right, and I'm going to call to the left positive y. And I would be talking about y displacements, y velocities, and y accelerations. You know, Giancarlo doesn't put the y in there, but I put it in there because we're going to be dealing with x and y, and maybe even z later on. So we may as well get used to it now that you have to specify which axis you're measuring the motion with respect to. Finally, I'm a little lost on how one would show that an object is decelerating. Is there a symbol to show this? No, there's no symbol, but if you think about it, deceleration always happens when your velocity and acceleration have opposite signs, at least for one-dimensional motion, right? If I have a positive x velocity, but a negative x acceleration, that means my velocity is trending towards going that way. That means I must be slowing down. That's deceleration. If I have a negative x velocity, I have a positive x acceleration, my velocity must be trending more towards that direction, and I got to be slowing down to do that. So if they have opposite signs, velocity and acceleration, that's always deceleration at that instant in time. Okay. Other questions, comments before we go into the last couple of sections? If you didn't get a chance to do, I did post the reading a little bit late yesterday. So I said, you know, if you want to do your reading responses this weekend, that's fine. Just try to read it as if possible, because we were going to cover it in class today. I don't remember exactly which subsection this is, but the kinematics equations, what people usually call the kinematics equations, specialize to describing motion with constant acceleration. And we're going to stick to one-dimensional motion. We'll get into two-dimensional motion in chapter 3. Okay, and they always assume, you know, here I'm going to assume we're moving along the x direction. So let's assume x acceleration is constant for a period of time. Nothing's acceleration is constant forever, right? I mean, it would just keep going faster and faster and burn up. But maybe between a few, you know, for a few seconds, it might be constant. So if the something's moving on the x-axis and its acceleration is constant between t equals 0, we're going to call that the initial time, and some later time that we'll just call an unspecified time t. And we'll always have to be careful about specifying in a physical problem what's the initial time and what's, we might call this the final time t. If that's true, then a couple of equations follow from that, and they follow by using calculus. So if you've done some integration before, you might be able to follow a derivation through here. We're not going to talk about it. We're just going to pull the equations out of thin air, but they come from integrating the equation that assumes that ax is a constant. dv dt equals ax, or, you know, if that means anything to you, and then you have to integrate that using your knowledge from calculus. But we're not using calculus in this course. One of the things that follows that says, so what we want to find out is if my acceleration is constant as a function of time, how does that tells me how acceleration changes as time goes on. It doesn't change because it's constant, right? How does my velocity change as a function of time? Can I write Vx as a function of t? And the answer is yes. Here is the function. Vx is this function of t. Notice there's a t on the right-hand side. So it's telling me how Vx is changing for every time in between the initial time and the final time. Okay, let's break it down. What are the symbols that are in here? So anytime there's a little subscript 0 in the subscript, that means the initial. And initial means at time t equals 0. So we're always going to say, if there's a period of constant acceleration, let's take the initial time to be, by definition, time t equals 0, and the later time to be that other time t. When you see a little 0, and I think Giancarlo uses the same notation I'm using here, that means what velocity x component did I, or x velocity did I have at time t equals 0? And the acceleration is whatever your constant acceleration is. T is how much time elapsed between the initial and final time. And Vx then means what is my x velocity at the final time. So it tells me how to move from the initial time to a final time, as long as the acceleration was constant between. It's got to be constant the whole time in between there. We're going to spend some time doing problems with this, but just talking it through. Here's another one you can get by integrating. You start with this equation. If you know some calculus, you might be able to integrate both sides if you really were paying attention in calculus. And you get equation 2 here. So we said we know acceleration is constant in time. Here's how velocity changes with time. It's a linear function of time. Position, how does position change with time? Oh, it's a quadratic function of time. That means there's a t squared in there. It has a t squared in it, so it's a quadratic function of time. Again, what do the symbols mean? The x0 means the position of the object at time t equals 0, where it was initially. X is where it is at that later time. That tells us where the final x position. And again, Vx0 is the initial velocity. That means at time t equals 0. Ax is the constant acceleration. And in a lot of problems, you'll know these things. You're just going to plug them in.
What is the significance of that being a quadratic function of time applies to t squared?
It's because, you know, when your acceleration is constant, right? It's sort of like your velocity is going up linearly with time. So that means if I wait 1 second, maybe I start at rest. I wait 1 second, my velocity is 2 meters per second. If I wait 2 seconds, I'd be at 4. If I went 3, I'd be at 6. If I wait 4, I'd be at 8. So it's going up linearly. If we plotted those, it would be a linear function. Now, if my velocity is going up, that means that every later time I have a higher velocity and my x, the rate of change of x is going faster and faster and faster. So the rate at which my x is increasing just goes up and up and up rather than increasing linearly. I don't know if that addresses exactly the quadratic, but qualitatively, that's what it's going to tell you as opposed to linear. Okay, there's a third kinematics equation, and I'm assuming that Griffiths shows this one too. It's not really independent. Here's what you do to get the third one. Notice that this is a relationship between Vx and t. I could think of it that way. I could pretty easily solve that for t equals, right? I would subtract off the Vx0 from both sides and then divide by x, and I would have t equals on one side. And t would equal some mess on the other side. And I would take that whole mess and substitute it in for the t here and for the t that's being squared there. And then I square out the big mess and simplify a lot. And when you do that, notice I've put in some stuff that had no t's in it everywhere there was a t. So there's not going to be any t's left in that equation. After the dust settles, it takes a little bit of work, you can work it into this form. So this is kind of a nice equation. It's not independent of these two. It's just a combination of these two equations. But it tells me not how Vx changes as a function of t, but rather how Vx changes as a function of how far I've gone since time t equals 0. Notice x minus x0 is my displacement from t equals 0 to the later time that we're considering, during which the acceleration was constant. So maybe I don't know anything about time. If I don't know anything about how much time elapsed, I'd be really tempted to look at this equation because I don't know anything about time. I don't want to have to solve for it first and then plug it in there. So we'll think about it that way. Okay, and again, Vx0 is the initial velocity. This is the velocity after you've moved through this displacement. And sometimes we'll write this as delta x because the final x position minus the initial x position is just the displacement between initial and final. So I'll write that as delta x a lot of the time. Okay, so again, that means Vx is going to be a linear function of time. X is a quadratic function of time. And you know from your math classes long ago, that's a parabola. So if we were to draw those just for some examples, here is a, notice I'm plotting, or I stole these from the web, obviously, but I'm got acceleration, AX, as a function of time. So here's a constant positive acceleration. That's good between these times that's shown on the graph. That means that the velocity is going to be a linear function of time, and the position is going to be a quadratic function of time. Notice the parabola is opening up. What do you look for in a quadratic function to know whether the parabola is opening up or opening down like that? Do you remember if you have ax squared plus bx plus c and you plot y as a function of x, how do you know whether your parabola is going to look like this or like this? Because this one is like this. Yeah, you look at the coefficient of the quadratic term, and if it has a positive coefficient, that's 1/2 ax here is the coefficient of t squared. That's the quadratic coefficient. So that means if AX is positive, the coefficient of t squared would be positive, and it will open up. Hey, the acceleration is positive. That's what this graph is assuming here, and that's why this one's opening up. Contrast that to this. Here is a constant negative x acceleration for the whole time period that's being shown, and we've got a parabola that opens down. Okay, we're not going to think about the parabolas too much in here. The only case where that's a little bit of a lie, it's not actually a parabola, is it is true that if your acceleration is 0 for the whole time period, it's still technically constant, right? So I mean, that's a case that we're talking about. And if the acceleration is 0, so here's a graph where the acceleration is 0. Notice that the quadratic coefficient is 0, and that means this is not really a quadratic function, it's actually a linear function there. So in some degenerate cases where there's no acceleration, we can still apply these equations, but you won't see the parabolas anymore. Okay, that's all good, but the rubber really meets the road when we start solving problems. So let's talk about how to apply these in problems and do a couple of example problems. First of all, some things you got to be careful in using these. Notice there are x coordinates and vx, and we already know that those depend on knowing exactly which way the plus x axis points. And maybe if you're using x coordinates, you got to know where x equals 0 is too, right? Vx is going to be positive or switch to negative if I change my mind about which way the plus x axis points. And x is going to have a different meaning if I change the origin. So in a particular problem, if something is moving, you've got to say, oh, right when the baseball was hit, I'm going to call the point where the contact happened. Let's call that x equals 0. And the direction the baseball was moving, that's going to be plus x. That's being very definite about which way is plus x and where is the origin. Okay, we'll see that in just a second in an example. We also have to be very clear, since we're assuming the acceleration is constant between t equals 0 and some later time t. When is that initial time that we're always going to call t equals 0, and when's the final time? Maybe I'm going to say initial time is right after the baseball was hit, and the final time is when somebody catches it, midfield or something like that. Okay, and always you have to be sure that AX is constant in between. If AX isn't constant, we can't use these equations. These are the constant acceleration kinematics equations. All right, once we've done that, we have to look at our problem and say, well, what was given? We're given some things, and there's always something we want to know. We would like to choose an equation that has the things we're given and has the things we want to know, and doesn't have anything else in there that we don't know about. That would be the ideal case, right? Then we can just plug in and solve for the thing we want to know. Here's an example kind of where that happens. And here we go. Thought I brought some of these to pass out. So we're going to do this problem 1 together just to sort of get the idea. We'll see if we get to problem 2 on here, but we're just on the front sheet today. Could you pass these straight back along the rows? So here is someone, I should have said it on here, but someone putting a golf ball towards a hole. The green is completely horizontal. They're not on a hill. I should have probably written that in this problem. Or at least that's what I was thinking of when I was doing this. A golfer puts her ball towards the hole. The ball's initial speed is 2.52 meters per second. And it decelerates. That means as it's going towards the hole, it's slowing down, right? Because, the green causes a little bit of kind of friction or something like that. It's going to slow down as it rolls across the green. And so it decelerates at 0.65 meters per second squared. That's the magnitude of the acceleration, but we mean it's slowing down until it comes to rest, or it makes it in the hole. So the question here is, given that initial velocity and that acceleration, will it make it to the hole, which is 4.8 meters away? So our plan is going to be, forget about the hole. Let's just see how far it goes before it comes to rest. And if the distance it goes is greater than 4.8 meters, we're going to say, well, it would have hit the hole and gone in before then. But if it's less than 4.8, we'll say it didn't make it. Okay, so I think most of this I worked out. Uh-oh. Lost my fancy clicker here. Here we go. Most of this I've worked out on here. So we've got to pay attention to these things up here. Which way is plus x? Nobody's telling us in this problem which way is plus x. There's no x-axis marked out on the golf course. So it's up to you to be definite about it. But you want to make your life easy. In this case, the ball is moving towards the hole, and why make my velocity negative when it could be positive? So I'm going to choose plus x to be the direction the ball is moving while it's slowing down. Now notice if I take Vx, so in this little cartoon here, I'm saying, here's where the ball is hit. Uh-oh. This technology of these virtual pointers hasn't quite matured yet. Here's where the ball is hit. Here's the hole over here. Maybe I'm imagining it stops before it gets to the hole in the cartoon I've drawn here. Let's call the direction from the hit to the hole plus x. So the plus x axis is in that direction. Wherever I put the x with the little arrowhead, that's the positive x-axis. Sometimes I'll put a plus sign next to it, but you don't have to. And just for definiteness, I'm going to take x equals 0, the origin on that axis, to be where the hit occurred, just to be sure about that. I've also got to say when's t equals 0. Well, again, when the hit took place, that seems to be a sensible time to call the initial state. Anybody have an idea of when we might want to do the final? If we're ignoring the hole and we're just waiting to see when the ball comes to rest. Well, the ball's going to come to rest after a finite amount of time. Why not just say whatever that time is when it first comes to rest, that's going to be our final time by definition. So I'm explaining what these things are in terms of the picture and the language of the problem, right? We've got a picture of a golfer here. We've got to explain x equals 0 plus x, t equals 0, and the later time t, the initial time and the final time in terms of the picture. Okay, and sure enough, we're told during that time it has constant deceleration. So it's slowing, 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 it comes to rest, maybe before the hole, or maybe it would have gone past the hole, and then we would say it goes into the hole. Now our job is to, well, we'll do that in just a second, but once I've chosen those things, come on. There we go. Once I've chosen those things, okay, well, let's read the problem here. I didn't read it. If the direction from the putt to the hole is plus x, what are the initial x velocity and accelerations? Well, I've chosen my plus x axis so that my Vx is going to be positive. And its initial speed was 2.52 meters per second. That's given in the problem. And so that means the initial x velocity is plus 2.52 meters per second. Everybody okay with that? Those plus and minus signs really make a difference, but this one's pretty easy. More to the point, if I've already taken the direction the ball is traveling to be positive and it's decelerating, what's the sign of its acceleration? It's got to be negative. That was one of the things we said earlier. It's decelerating, or we would say its velocity is trending towards the negative direction. If it's moving in the positive direction and its acceleration is negative, that means it's doing its best thing to get towards a negative velocity, and the first thing it's got to do along the way is stop, come to a rest. So it's slowing down. So it's a negative acceleration, and the magnitude of the acceleration is 0.65, but I got to put that minus sign in front of it. It's all important. We'll get completely the wrong number if we don't get that minus sign in there. Okay, so that's the information that's given, and now what do we want to know in this case? How far it goes, right? X initial is 0, so we kind of want to know X final. Or X final minus X initial, that would just be how far it goes. It's X displacement, either one. All right, so let's look at 3 now. Choose an equation that involves what you know, I put that in a box there, and what you wish to know. I wish to know X final, right? That's where it's going to be when it comes to rest, if that's what final means. Which equation involves what I know and what I want to know and doesn't involve anything that's difficult to know from this problem? Anybody have it? I guess in terms of the first, second, or third equation there, do you have any intuition about which way we could go, do the least work? Yeah. The third one, because we don't know anything about how much time it takes to come to rest? If we wanted to, we could figure that out, but we don't want to know it and we weren't given it, so I'd rather avoid the t. So let's just look at this third equation here, which is written here, and this is just a scan of my solution that I've written out, and I always post the solutions to these on the website. So the things we do in class, I'll write out my solutions and put them in that middle column of the website so you can review them later. Here's the third equation. Remember, I wrote this as x minus x0, but that's the same thing as the x displacement, so I just wrote it here. And the idea is, if I know the displacement, that's how far it went between t equals 0 and the stopping point. So that's exactly what I want to know. Delta x is the variable I want to solve for here. Do I know everything else in here? Do I know ax? Yeah, it's in the box there, right? Do I know vx initial? Yeah, it's in the box. Do I know vx final? It's not in the box. Do I know vx final? Yeah. It's 0 because by definition, I said final time is going to be defined by when it comes to rest. So that's important that I was clear about that and said, my meaning of final is when it comes to rest. It's decelerating, constant deceleration the whole time, so we're justified in using these equations. Final means when it comes to rest. So what is its final x velocity? 0. So this is going to be a 0 squared in there. Let's plug those numbers we know in. I plugged them in, and the only unknown is delta x. And okay, most people are pretty okay with solving equations like that, where there's, it's not in a quadratic equation. All I have to do is compute this number, put it over on the other side with a minus sign, and then divide by this negative number, 2 times negative 0.65, to get delta x equals. Anybody want to see that? Some people, it's been a long time when they're doing algebra, how to get from the left side to the right box there. Let me know if you need more help with that. We'll have a lot of practice, but my tendency is, unless it's a quadratic equation or something, but there's no squares on this, so this isn't too bad to solve for, but some people are a little bit rusty in physics 110. Okay, so that means if the hole weren't there, it would go 4.88 meters. Now we know there was a hole in the way, and we're assuming the putt's going in the right direction. It's not missing the hole. So I would conclude in this case that it makes it to the hole, assuming it's putted directly toward the hole. Okay, that's a constant acceleration kinematics equation example, and we'll do a lot of them as time goes on. Any questions about that? Okay, so you got to know acceleration is constant. In this case, it's at least not unbelievable that the ball has constant deceleration as it goes towards the hole. But there's one example that you read or will read about at the end of the chapter where constant acceleration happens all the time. And that's one of the reasons why these constant acceleration kinematics equations are so important. And that is what's called free fall motion. So free fall motion, and we're usually going to be thinking of things free falling near the surface of the Earth, means an object. We haven't talked about forces yet, but most people are okay with gravity being a force, and it's pulling this ball down as I drop it, right? The important thing for free fall is that while it's falling, it's not in free fall while I'm holding it, because my hand is pushing up on it. I'm using your intuitive notion of forces. We'll spend a lot of time talking about forces later on. Here's a mass right here. I'm pushing up on the mass. Gravity's pulling down on it, and they're sort of opposing each other and balancing out. But once I let it go, gravity is essentially the only force on it. Now, that's not quite true, because as it's falling down, it's falling through the air, and the air is kind of pushing back against the direction it's going. That's called an air resistance force. For this dense brass mass, the gravitational force is really big and the air resistance force is really small. So we're just going to pretend that the air resistance force doesn't matter. And so in that case, let's just read the text here. Near Earth's surface, every object in free fall, that means gravity is the only non-negligible force acting on it, will accelerate towards Earth. I could see it accelerating towards Earth, right? As I dropped it from rest, it went faster and faster towards Earth. So it's accelerating towards Earth with the same magnitude acceleration, and the direction is towards Earth, but the magnitude of acceleration is called little g. Little g. Sometimes that's called the gravitational field, but we won't call it that. We'll just call it the gravitational acceleration. And it's the magnitude of the acceleration is 9.8 meters per second squared. If you've ever taken a physics course before, you've certainly seen that. So the claim is it doesn't matter about the mass. As long as gravity is the only significant force, so this is a pretty dense piece of metal right here. Here's a bouncy rubber ball, but it's quite a bit less massive than the piece of brass. And if I do my best to let them go at the same time, we should see that they accelerate at the same rate and therefore hit the floor at the same time if I release them at the same time. Okay, so it doesn't matter about the mass. It doesn't matter about how big the object is, as long as we can still ignore air resistance. The problem is when things tend to get big, air resistance can be bigger, and they have to be really massive before we can ignore air resistance. Okay, what would be an example of something where that's maybe not the case? Here's a little cube of styrofoam. Oops. Let's do a little race between the bouncy ball and the cube of styrofoam, for which the gravitational force isn't very big. It's really easy for me to hold up the styrofoam. So that means the air resistance force doesn't have to be very big to compete with it, to make it non-negligible. So let's drop these two, see if we can tell the difference. You see the bouncy ball 1. So generally when things are kind of dense, the mass is put into a fairly small volume, we can kind of ignore air resistance. Although if you drop something from a tall skyscraper, eventually it's going to be going fast enough that that air resistance force gets bigger and bigger the faster it goes. You know, this Kroger bag that I brought things in, almost instantaneously, it's not accelerating anywhere near 9.8 meters per second squared. So, all right. So that's free fall. And so that's a case where acceleration is going to be constant all the way from when I drop it. And it's going to be 9.8 meters per second squared in that direction. And in fact, it sounds strange, but free fall doesn't have to be just when it's falling. If I throw something up and acceleration is negligible the whole way, air resistance is negligible while it's going up, when it reaches the top and then it starts coming back down until it hits the floor, then there's another big force on it. But as long as it's in the air, we would call that free fall. Even during the part where it's rising, I would still call it free fall, strangely enough. Okay, let me just illustrate that with a couple of pictures. Okay, acceleration is the same regardless of the object's mass, but air resistance must be negligible. So generally, dense objects that aren't moving too fast. So here's someone dropping a ball from a cliff. The claim is that right after it's released, not before it's released, because there's another big force on it, the hand force that's competing with gravity. But as soon as it's released, it's accelerating towards Earth at 9.8 meters per second squared. A little while later, as long as we can still ignore air resistance, it's at 9.8 meters per second squared. Everywhere in between, it would. Now, eventually, air resistance is going to get pretty big. And at that point, its acceleration might start to fall off a little bit smaller. Here's someone throwing a ball up, and then it comes back down. And the magnitude of the acceleration is 9.8 in the direction downward. So it's slowing down on the way up and then speeding up on the way down. Both of those are accelerating towards the Earth. Same acceleration on the way up for that instant when it's at the very top turning around, and on the way down, the acceleration doesn't change. Now, we've been talking about x acceleration. We've got about 2 minutes left here, but this is a good place to stop. We've been talking about x accelerations, and the x accelerations are what appear in those kinematics equations, right? I might have an ax times t squared in the x equation. How do I do that? Well, I got to know what my x-axis is. Maybe I choose, because I'm free to, there are no real axes in the world, I'm going to take plus x to be up. I don't care what Giancoli says about the y-axis. I'm going to take plus x to be up. And in this case, what that means is it's accelerating toward the Earth. In other words, it's slowing down on the way up and it's speeding up on the way down. That means my x acceleration is negative. So notice the minus signs I put in front of those accelerations. It's once I've chosen plus x to be up, it's accelerating downward. That's in the negative x direction all the way through that motion. And if I plug into the kinematics equations here, When I plug in that AX, I've done that down below, I've got to put a minus sign in there for my choice of x-axis. Once I've chosen that x-axis, that needs a minus sign. Of course, the x-axis is also going to inform the sign of the velocity and all that kind of stuff. I'm free also to choose plus x to be down. So I just flipped the only thing that changed here was I chose now plus x to be down. There are no real axes, so I can choose them any way I want. Now all my axes should be positive because its velocity is always trending more and more positive. On the way up, it's slowing down. That's the best way to trend positive. And on the way down, it's going faster and faster. That's trending more positive too. And so if I plug into the kinematics equations with that choice, these should all be plus there. Okay. Do we have time to do this? Yes, we do. We can do it in 1 minute. A stone is launched by a slingshot straight upward at 12.6 meters per second. That's right when it leaves the slingshot. Ignoring air resistance, what maximum height above the launch point does it reach? Let me choose some conventions. I decide to choose plus y is that direction. Y equals 0 is the point where it just leaves contact with the slingshot. So that's the point at which gravity is the only significant force on it. And we'll ignore air resistance because it says to. So we'll call y equals 0 the launch point. We'll say right after it leaves contact with the slingshot, that's t equals 0 by definition. And when it momentarily comes to rest at its highest point, that's going to be my final time, the later time t. Okay. And what do I know here? I know my initial y velocity, that's there. I know my y acceleration is negative because I chose plus y to be up. It's negative 9.8 because I chose plus y to be up. And I know my vy final is 0 because I chose the highest point to be the final point. And at that point, it's momentarily at rest, right when it's sort of in the process of turning around. It only happens for an instant, okay? And then I just look and say, which one of those equations is going to tell me directly using the things I know and what I want to know. And what I want to know in this case is how high does it go? I want to know either delta y or y. I don't know anything about t, so I'm going to choose the same equation as before. I'm going to choose that equation, and you plug in what you know, and you can figure out what is its y displacement between the initial time, that was when it was released, and the final time, that's when it momentarily stops before coming back down. All right, we'll continue with this on Monday. We have to delve into some more complicated kinematics problems that we'll do with free fall. So keep that worksheet with you, bring it on Monday. We'll do the problem on the backside, and we'll wrap up with a little stuff, and then we'll get into chapter 3. So that chapter 3 reading, don't forget to do that this weekend. Hopefully the ice melts. It's not looking too hopeful right now, but maybe we won't get any more ice, and that'll be considered a win.
Dr. Kelly?
I need to change it. No, I think I did change it. I believe it's due Wednesday now. I wanted us to finish the discussion on Monday and then have a couple of days to ask questions and just think about it.
Dr. Kelly? I got like 2 quick questions. I don't understand how if you're throwing the rock upwards and like y plus is upward.
Nafis, are you talking to me?
Yeah.
Okay, can you just hold on a second because someone in the room is asking a question, and I'm going to answer that question and then I'll get to you.
Great.
So just hold on for a second. Yeah, continue.
Like b naught equals 0, or is it always that b naught equals the actual?
Yeah, it's only, v0 x or something. It's got to be, I've got to choose an axis direction. But if I did a problem where I dropped a rock from rest and I said, oh, I'm going to take t equals 0 to be right as soon as I released it, then its initial velocity would be 0, right? Because I'm releasing it from rest. But if I throw it up like that, right when, and my initial is when I release it, it's already moving when I release it. So you got to think about what's happening at t equals 0. Sure. All right, Nafis, go ahead.
I don't get how if y plus is upwards and you're throwing the rock upward, like why would acceleration be negative in that situation?
It's for the same reason. I mean, let me go in front of the camera here. It's the same reason that, you know, I said, if I'm moving in the plus x direction, but I'm slowing down, right? So let's take plus x to be, in my view of the board here, to the right. And I'm moving to the right, but I'm slowing down as time goes on, right? Is my acceleration positive or negative, my x acceleration? Well, the answer is
Negative.
it's negative. If I'm moving in that direction and my if I'm moving in the positive direction and my x acceleration is positive, I'd be going faster and faster as time goes on, right? So
Yeah.
if I'm moving in a certain direction and slowing down, what that means always is that my velocity and my acceleration have opposite signs. All right,
Okay.
so going to the problem we're talking about, we chose plus y to be up. Here's a ball going up, and it's slowing, slowing, slowing as it goes up, right? As it slows and slows and slows, right? If it's moving in the plus y direction and its y acceleration was positive, it would be blasting off faster and faster in that direction. But I guess one way I would think of it is it's slowing down in the positive direction, and that's the best it can do on the way to trending towards a more negative velocity. If it's trending towards a more negative velocity, its y acceleration is negative. That's one way to remember that.
Okay. That clears it up. And then just one more question. The reading for 2.5 to 2.8, you said it's due on the, like, when you said weekend, did you mean by like Sunday or by like tonight, Friday?
No, I mean, I think I put on there, at least in the email I sent to you, by 8 a.m. on Monday morning. I said by 8 o'clock a.m. on the next day of lecture.
Okay, great.
You know,
All right.
normally in previous semesters, I would have had it due by midnight on Sunday. Some people said, you know, I just stay up really late and sometimes I like to do things at 3 a.m. Fine, it doesn't bother me. I just want it done by the time I get to my office so I can start looking at your reading responses and maybe react to them that day in class.
Yeah. Okay. Thanks, Dr. Kelly.
Hey, no problem. Good seeing you and have a good weekend.
You too. Thanks.
Thanks.